Hello dear students, welcome to the channel Pen and Paper Chemistry on YouTube. The topic that we are now taking up is electrochemical series. If you've been following the channel, you will observe that we've already dealt with galvanic cell, we've spoken about the EMF of a cell, and now we are going to move a step further. Electrochemical series, as the name indicates, it's just some kind of an arrangement. So what arrangement is that? It's based on the electrode potential of the elements. How do we arrange the elements on the basis of their electrode potential? For that we will follow certain rules. First, we will represent all reactions as reduction reactions. If you remember from the previous video, we had mentioned that the IUPAC laid down the rules, and the first and most important rule that they laid down was that we are going to represent the reactions as reduction reactions if we want to talk about electrode potential. Just to do away with the confusion that one person is saying oxidation potential, the other is saying reduction potential. So in order to remove that confusion, we say we will represent all reactions as reduction reactions when talking about electrode potential. Second point, all potentials that we are going to depict over here are reduction potentials. Very obvious. You'll say it's the same point being repeated. Yes, because we want to stress on that point that the potential, if I am using the word standard potential, so standard potential, unless we specify standard oxidation potential, it is assumed that standard potential would mean reduction potential. Potential means capacity, ability. So reduction potential means the potential to get reduced, the potential to gain electrons. So more the reduction potential, more is the tendency to get reduced, right? In other words, that gives us the third point. Higher the reduction potential, more is the tendency to get reduced. In other words, if it is itself getting reduced, it will oxidize the neighbor very easily. So, higher the reduction potential, more is the capacity to get reduced, better it is as an oxidizing agent. If itself it is getting reduced, it will oxidize the other substance more easily. So, more the tendency to get reduced, better is the capacity to oxidize the other substance. And vice versa, lower the reduction potential, more is the tendency to get oxidized. Yes, more is the tendency to lose electrons. Hence, it will allow the other substance to gain that electron so easily, and this will become a better reducing agent. So we have, if you are given two electrode potentials, I come back to my favorite example, zinc negative 0.76 volts and copper, yes, you also know it by now, 0.34 volts. So zinc is negative 0.76 volts and copper is 0.34 volt. Now out of the two of them, if you are just given the electrode potentials, how do you decipher which one is going to behave as the anode, which one is going to behave as the cathode? Yes, the lower one, the one with the lower reduction potential. So negative 0.76 is smaller than 0.34 volts. Please do not ignore the sign. So here what we'll have is zinc will behave as the anode, it will have tendency to get oxidized and it is the reducing agent over here. On the other hand, copper has a higher value of electrode potential, it will behave as the cathode, it will get reduced itself and it is the oxidizing agent over here, right? So what we've done over here is, the elements are now listed over here in this series in the order. Can you see in what order I have listed? Are they increasing or are they decreasing? See here, 2.87, 1.81, 1.36 and so on. Whereas after hydrogen, what is the electrode potential of hydrogen? Correct, it's 0 volt, arbitrarily chosen as 0. The reduction potential of hydrogen is 0. For iron, it is negative 0.44, magnesium negative 2.36 volts. So what is happening is the standard electrode potential. And which potential is it? Reduction or oxidation? Perfect, it's the reduction potential. So what we have done in electrochemical series is arranged the elements in the order of their decreasing standard reduction potential. How do you know that it is standard? Yes, you see the small 0 sign on the head. Sometimes you'll see it like this as well. Denotes the standard conditions, 25 degrees Celsius. If it's a gas, then 1 atmospheric pressure, concentration 1 mole per liter. We have already spoken about this earlier. So we are talking about the standard reduction potentials over here. So electrochemical series is the arrangement of elements in the order of their decreasing reduction, standard reduction potentials, right? Now, the question that arises, ma'am, do we have to learn all these values? No, you are not supposed to by heart these values. These values are provided to you in case you are asked any question, and these are readily available in a tabular form in any of the chemistry textbooks that you can lay your hands on, which covers the topic of electrochemistry, right? How will I use this electrochemical series? You've already started using it. Yes? You are already able to give me the answers of 2 questions based on this electrochemical series. Let's say now if you notice over here, I put these dashes, these dashes. So we start this electrochemical series with fluorine, which has got the highest reduction potential. That means it's the best oxidizing agent, and ends at lithium with the most negative reduction potential. Hence it's the best reducing agent, right? Now, I've listed the first one, fluorine. Next is cobalt, gaining 1 electron. Then there's a dash because this space, I don't want to make it very crampy by adding all the elements. So I have just spread them out and given them to you in gaps. So there's chlorine, there's bromine, there's silver. There are many more elements and reactions in this electrochemical series. I've highlighted hydrogen over here, which is 0 volts, right? Then iron, all the other metals will come here, magnesium, lithium, and so on. So, based on the third point, let's suppose I have to compare chlorine and bromine. Give me the answer now, which of these will, if supposing we put together ions and element of chlorine and ion and element of bromine, which of the 2 out of chlorine and bromine will behave as the cathode, which will behave as the anode? Go ahead, just see. Higher the reduction potential will behave as cathode, right? And perfect. So chlorine will behave as the cathode. It will get reduced. It will oxidize bromine. So what will happen over here is bromine will get oxidized, whereas chlorine will become the oxidizing agent. Go ahead now. Let's say we compare iron and magnesium. Which of the 2? Now both of them have negative values. So which one of these is higher? Which one is lower? Perfect. Negative 0.44 will be bigger than negative 2.36 volts. Sorry about that. Minus 2.36 volts is smaller than minus 0.44 volts, right? So iron will behave as the cathode and magnesium electrode will behave as the anode, like we have seen in the case of zinc and copper as well. Of course, there we had the combination of one positive and one negative. Now, we have expanded, once you understand this concept, you will be able to relate to any of the points that I am going to do further. The oxidizing agent, the reducing agent. So what we are saying over here is that if it has got higher reduction potential, that means it is a better oxidizing agent. So if you have to compare fluorine and cobalt, which is a better oxidizing agent? Obviously fluorine. And which is the best reducing agent? Correct. So what we can do over here is we can mark it by an arrow pointed upwards, saying that oxidizing property is increasing, right? At the same time, we can mark it down saying that reducing property is increasing, right? Oxidation property increases like this and reduction property increases from the top to the bottom. Let's go on to the next point after this. So I put it here a little more neatly. Oxidizing nature increases from bottom to the top. Reducing nature increases from the top to the bottom. Going down, reducing nature increases. Going up, the oxidizing nature increases. So looking at the electrode potential values in an electrochemical series, it is very easy for us to determine the oxidizing and the reducing nature of a substance. Simple mnemonics that we have discussed earlier. Lower reduction potential behaves as the anode. Oxidation will happen at that electrode. GRA, graph, good reducing agent. Simple, right? This way you can design any of your mnemonics, and maybe if you find something interesting, you can share it in the comment section. Most welcome to do that. So our fourth point, behavior as oxidizing and reducing agent, has been covered very thoroughly. We now go on to the ability of an element to exist, basically an element to exist as a metal or an ion, right? This is something that we observe. We know that silver, gold, platinum, all these elements can peacefully exist in nature without being affected by the oxygen, carbon dioxide, moisture of the air. On the other hand, if you have an element like iron, a metal like iron, you leave it exposed to the atmosphere, within a week you'll see that there'll be slight change in its color, and over a period of a month or so you will find reddish brown coating developing on it, right? So how can we explain it on the basis of its standard electrode potential? Go ahead. Yes. Lower the reduction potential, more reactive it is. Lower reduction potential of the metal. Now, for example, again, my favorite example, zinc and copper. I think by the time we finish this lesson, even you will remember these values. Zinc you will find existing mostly as ion, right? It is very, very reactive. Copper, on the other hand, you will find it that it can survive the vagaries of nature for a much longer time compared to zinc. That clearly shows in their electrode potential as well. So lower the reduction potential, more reactive is that particular metal. Displacement reactions. Now here we have to see two examples. Forget about the last two. See over here, zinc. Zinc displacing copper, or copper displacing zinc. I will explain one more method how we can determine that. But for now, let us concentrate on their reduction potentials. Zinc has got a lower reduction potential. That means less tendency to get reduced. It has got a higher oxidation potential. It has got more tendency to get oxidized. It has more tendency to lose electrons and turn into an ion. Whereas copper has got a lower oxidation potential, it has got a higher reduction potential, it has more tendency to turn into a metal rather than remain as an ion. So out of the two reactions, which one do you think will occur just by looking at the reduction potentials? Perfect. The first one. The second reaction does not take place. Apply the same logic to answer the next two set of reactions. Which of these is feasible and which of these is not? You have KCl plus bromine giving you KBr plus Cl2. You have KBr plus Cl2 giving you KCl plus bromine. Look at the reduction potentials. Notice over here, bromine is turning into Br negative over here. So bromine is getting reduced. So which one will displace? So chlorine will displace bromine or bromine will displace chlorine? Perfect. It is the second one which will take place because Cl changing to Cl minus is 1.36. And Br negative changing to Br2, that will be minus 1.09, because I'm talking about Br negative changing to Br2. I'm talking about oxidation over here, so it will become minus 1.09. Now this is by looking at the electrode potential values. I'll explain you one more method. That's the mathematical method of determining whether a particular displacement reaction will take place or not. So get your pen and paper ready to do some numericals with me. Now let us see how we can use the electrochemical series mathematically in order to determine whether a particular reaction will take place or not. Again, I've taken my favorite example. Cu plus ZnSO4 gives you CuSO4 plus Zn. We have to check, we're not sure as yet, we have to check whether this particular reaction is feasible or not. Feasible means whether it will take place or not. So what do we do? Yes, you can tell me that it will not take place. I agree with you. Now let's suppose you have to prove that mathematically. How do you do that? So we've got the reaction that is taking place over here is copper changing to Cu2 positive. That means copper is undergoing oxidation. On the other hand, zinc ion Zn2 positive is changing to zinc. So it is undergoing reduction. The net cell reaction that we are representing over here is Cu plus Zn2 positive gives you Cu2 positive plus Zn. Now go back to what we had done earlier. Oxidation means anode and reduction means cathode. Yes, it is listed also over here. Loss of electrons, oxidation, anode. I have taken a full lesson on this. In case there is any doubt, please go back to the EMF of a cell and make the fundamentals clear before you proceed. Zn2 positive changing to Zn, that means gain of electrons, reduction, cathode. Standard EMF of the cell, E naught cathode minus E naught anode. We use the reduction potentials over here. So minus 0.76 minus 0.34 volts. So these are the reduction potentials that have been provided to us. Now if you notice over here, we get a value of minus 1.10 volt negative. Negative means that this particular cell reaction that we are talking about is not feasible. It cannot take place. It's a negative value. So let's try the other possibility. Zn plus CuSO4 gives you ZnSO4 plus Cu. Now you try and determine the E naught of this particular cell. Yes, it will be opposite 1.10 volts. So Zn changing to Zn2 positive and Cu2 positive changing to Cu. So here we have zinc behaving as the anode and copper behaving as the cathode. So E0 cell will be, yes, reduction potential of the cathode minus reduction potential of the anode, which gives us a value of 1.10 volt, which is positive. Yes, this reaction will take place. Now this type of a question will help you to explain quite a lot of objective questions also. For example, you get a question, can we store a solution of copper sulfate in a vessel made of zinc? Yes or no? Yes, why? How is it yes? Yes, because you are saying that it is reacting, but if it is reacting, that means zinc is displacing copper, then should you or should you not store? Perfect. So have that clarity of thought in your mind. It's a very easy concept. I keep repeating, it's a very easy concept. So because zinc is displacing copper, it is reacting with copper sulfate, so I cannot store. Yes, in this particular question, if the reaction is taking place, that means I cannot store a solution of copper sulfate in a vessel made of zinc. Supposing I change the question, can I store a solution of copper sulfate, let's say in a vessel made of silver? Prove it mathematically. Try this question yourself, because the reaction also will change, because now it will become Ag2SO4, right? But remember that the value of the EMF does not get multiplied. We do not multiply it by the stoichiometric coefficient. So if supposing I have Ag2SO4 plus copper over here, of course, in order to balance the reaction over here, we'll put 2. The EMF of this, the electrode potential of silver is 0.80 volts. Let's suppose. Then what will be the EMF of this cell? Let's try working it out. E0 of the cathode minus E0 of the anode. Now here, what will act as the cathode and what will act as the anode? Cu2 positive changing to copper, it is behaving, it is undergoing reduction. Cathode silver is changing into silver ions, it is behaving as the anode. So cathode we've got is 0.34, right? Yes, this is what I was talking about. We will not multiply the 0.8 by 2 because it's an intrinsic property. 0.80 volts is, that's it. If there is a 2 over here, you do not multiply by 2 here. Negative 0.80 volt. This gives you a value of, go ahead. Now this is a positive or a negative value? Negative value, correct. So minus 0.46 volts. So negative value means, does this reaction take place? No, it doesn't take place, right? So because this reaction does not take place, can I store a solution of copper sulfate in a vessel made of silver? Yes, we can. Perfect. Now we will also explore and also try and explain the behavior of metals vis-a-vis hydrogen. We have seen in the activity series of metals that there are certain metals which displace hydrogen from its compounds, whereas there are others like silver, copper, etc. which do not. We'll try and explain that with the help of electrochemical series. Keeping the electrochemical series still on the board, I have now given you 2 reactions over here. Zinc displacing hydrogen from its compound. So I'll have Zn plus HCl giving me ZnCl2 plus hydrogen. The other possibility that we are exploring is copper plus H2SO4 giving us copper sulfate and hydrogen. Now you have the values for the electrode potential of zinc, copper and hydrogen here. Zinc of course is negative 0.76 volts. Now go ahead and give me the possibility of these two reactions, whether they will take place or not. Simple. Pause the video, do the two parts yourself and then tally your answer. You'll actually enjoy the topic. Honestly telling you, in order to teach this topic, I actually don't have to revise and I don't have to really think as to what to teach, because it is such a simple topic. Once the fundamentals are in place, it's a cakewalk, seriously. So go ahead and do this numerical. Zinc changing to zinc ions, oxidation anode, hydrogen ions changing to hydrogen, so reduction cathode. Can you determine the standard EMF of this cell? Cathode minus E naught of the anode. Cathode over here is hydrogen. Please remember that we have to put the reduction potential values. So negative 0.76 volts and we get it as a positive value 0.76 volts. Does this reaction take place? Yes, it will take place. That means, does zinc displace hydrogen from its compounds? Yes. Let's see the second possibility. E naught cell. Now copper changing to Cu2 positive, loss of electrons, anode hydrogen, ions changing to H2 gas, so this is cathode. E naught cell is E naught cathode minus E naught anode 0.34 and I get a negative value over here. Now can you give me a generalization from this? E naught of the cell is negative, that means the electrode potential is negative, that means it does not have enough energy to do this kind of a work. If I want to do it, I'll have to put in some extra energy, so it does not become feasible. So that's a negative value. Does this reaction take place? No. So can copper displace hydrogen from its compounds? No. Now just look at the standard reduction potential of zinc and copper. From this, what generalization can you make about the behavior of metals to displace hydrogen from its compounds? Remember, the electrode potential of hydrogen is 0. Yes. Negative reduction potential means the element or the metal will displace hydrogen from its compounds. A positive reduction potential, that means a positive value or a value greater than hydrogen, shows that that particular metal will not displace hydrogen from its compounds. So if you see, this is very, very similar to displacement reaction, except that in this case we are specifically talking about displacing hydrogen. That's all that we are doing. So don't get nervous, oh there are so many points. There are so many points, but these are simply elaborated so as to make the concepts more clearer. That's all. There's nothing much in this particular heading. We shall, till now we've been talking about the standard values, right? We will now move on to the effect of concentration, temperature and such variables on the electrode potential of a cell, right? Till that time, 10 numericals please. 10, because there are a lot of concepts that we have covered. 10 numericals that you need to practice on this particular concept in order to be confident, in order to be able to teach it to somebody else and get a smile on their face. Stay subscribed. Take care of your health. Happy studying. Do subscribe for more videos in chemistry and don't forget to share the channel with friends and classmates. See you in the next video.